Okay, I hope that we will have a problem with computer in the next presentation. The presentation will be made by Motz. Okay, we have also the time. Please start.
Yeah. Thank you, Mr. Chairman. Good afternoon. My name is Marx. Mr. Motz is the head of our institute, and what I show today are the results of the PhD thesis of Dominic Rathmann, who actually wanted to present this 2 years ago. Now he's not anymore at our institute, so it's a pleasure for me to present these results. We are working on nanocrystalline and ultrafine grained nickel, and what we do, we make electrodeposition of nickel. Here you can see such an electrodeposited plate, and then we investigate the thermal stability against grain growth, the mechanical stability, we characterize the microstructure, and we are interested in the mechanical properties. For static and for cyclic loaded components, we need high toughness and high utility, and you may know we have 4 mechanisms to increase toughness and tensile strength: solution, solid solution hardening, dispersion hardening, strain hardening, and we have grain refinement. And the grain refinement has some advantages. It can be combined with the other mechanisms. It can also be realized without any expensive alloying elements. It also works for very small components, and it's the only mechanism to increase hardness and ductility. And you know these whole patch plots where we have the square root of the grain size, and here at this end we have the small grains, and here we have the larger grains, and we have an increase in hardness and an increase also in the yield stress. Yeah, what are we doing? We are producing our samples by electrodeposition. Here you can see a scheme how this looks like. This I have shown on the first slide. The thickness of the plate can be up to 2 millimeters, and the challenges are to get a nanocrystalline microstructure, to get a homogeneous microstructure for this whole 2 millimeters, and during the whole deposition process, which lasts 10 days, we want to have low residual stresses, and we need an appropriate specimen design because the amount of material is still low, so we do not produce huge plates. And we make it here by a pulsed electrodeposition. And we have a lot of influencing factors: our electrolyte, the additives, which is very important in our case, the temperature, pH value, the motion of the bath and the geometry of the bath, filtration, cathode material, deposition mode, and the current function, if you have direct current or pulsed current or reverse pulses, as you can see here. This is a huge variety of parameters, and we can use it also to tailor our specimen, our materials and microstructure in the and to tailor our microstructure. So first we want to know about thermal stability. Grain growth starts at 170 degrees C, which is not very much. So if you have a small overheating maybe in your components, you may get grain growth and changing mechanical properties by this. The grain growth is not continuous, it's abnormal. Some crystals grow preferentially, as you may see here. You have a nanocrystalline microstructure and some ultrafine grains in between. You can also use this to produce a bimodal grain structure. You can stop a heat treatment in between, and then you have a nanocrystalline ultrafine grained microstructure, which from literature is expected to be optimized against fatigue damaging. For further heat treatment, you get monomodal ultrafine grained microstructure, as you can see here, and for further heat treatment at higher temperatures, you will get a second stage of grain growth, again abnormal grain growth with some grains growing in the order of some of tens of microns and the others remaining in the ultrafine grained area. For the mechanical stability, we did some wear experiments. We started with two initial microstructures, one nanocrystalline and the other one in the bimodal structure, and we found at the surface in both cases we got the same microstructure. We find recrystallization due to the wear, and we get a mixed area of metallic parts and oxides from the surface mixed in this surface near area. To characterize our microstructure, we measure the size of the small matrix grains, the size of the abnormal grown grains, ratio of both grain morphology, texture, gradient through the thickness of the plate, and we do this by electron microscopy based techniques, backscatter electron images, EBSD or transmission. EBSD we also use for the small grains which are in the nano-sized area, and then we get here maybe this distribution, size distribution of such a bimodal microstructure with some small grains, and here about 400 nanometers. It's not micrometers, nanometers here. The grain size here of the ultrafine grains. We have done this through the whole thickness. Here there's a substrate. Here you can see it's quite homogeneous. We have a texture, as you may see from the color of this EBSD maps we have done, but we do not have any gradient in the grain size in this direction here. This is the microstructure for different heat treatments, 210 degrees C for different times. The blue curve is for very, very long time, and the first maximum here in the nanocrystalline area remains nearly constant. The ultrafine grained maximum shifts a little bit to higher grain sizes, but it's also in the area. Again, this must be nanometers here, not micrometers. Sorry for that. And after this long time, you get still some bimodal microstructure, but in the ultrafine grained region. This is due to twinning during the grain growth. The other one is because of this abnormal grain growth. The hardness during the heat treatment decreases, as you can see here. This is at 210 degrees C for different time, and this here is for 150 minutes for at different temperatures, and for both, in both cases we have grain growth and the hardness decreases with the temperature and with time, as expected. So what we have also done, tensile tests, and here the black line is for the nanocrystalline material as it was produced, and for the heat-treated material we expected to get more ductility because we have some larger grains. However, we have here found this red and the green curve, the red for the bimodal microstructure and the green for the ultrafine grained material. So the